Okay, in this video we shall see uh, what is logical effort and what is the importance of this topic, which is logical effort. Now the outline of this topic goes like this. So now we have the introduction of logical effort. So what is the delay? How do we calculate the delay in a logic gate? So how do we estimate the logic delay in a multi-stage logic network? We'll just take up an example and we shall see the summary of this logical effort. Now we know that chip designers face a number of choices like, okay, what's the best circuit topology for a function? So assume that you have a full adder. So full adder can be implemented in different ways. So now the chip designer has to select, okay, which is the best circuit topology for a given function like a half adder or a full adder, and how many stages of logic give the least delay, because we know that in most of the designs we are looking at minimizing the propagation delay of a circuit. Now how many stages of a logic gives the least delay is the most important thing, and in order to achieve that, how wide should be the transistors. Now we are supposed to properly size the transistor. Now this is what is these are the choices a chip designer has to make so as to minimize the propagation delay of any particular logic. This logical effort is a method to make these decisions. So using this logical effort, we can make the decisions, okay, which topology is best and how many stages are required and what is the dimension of the transistors. Now this uses a simple model of delay and allows back of the envelope calculations. So once we know what is the expected values, then we can just come back and see what is how do we modify the dimensions. Helps make a rapid comparison between the alternatives. So you can have different available circuits to implement the same logic. Then you can just easily compare, okay, which one is giving the least delay, so that can be a proper decision before you go for the final fabrication, and emphasizes remarkable symmetries, meaning that we can easily make the MOSFETs if we have a symmetrical symmetries while writing the layout. Now we know that we will going to certainly express the delay in terms of second, nanosecond or picosecond. So instead of specifying them in terms of a second, so we'll define a delay which is D, which is nothing but absolute time, which is in terms of second divided by the tau. So where tau is in terms of second. Now once you have this second divided by the second, we end up with the absolute time is in terms of second and tau is also in terms of second. We end up with a constant value. This delay, whatever we are writing, so we express the delay which is the independent of unit. So we want to simply represent this delay by a number. And what does this delay consist of? So delay has two components, that is D is equal to F plus P. So where this F is given by the effort delay, so which is given by G into H. This is also known as stage effort, because we know that in order to achieve a particular goal, we're supposed to have different stages. So this F is nothing but the stage effort. What is the effort given by each of the stage? So this F is given by G into H. This F is again divided into two components, that is G as well as H. Now here we can see this is a delay which has got two components, one is F, other is P. So this F is nothing but the effort delay, which is again further divided into two parts, which is G as well as H. Right, has got two components G and H, where you can see G is written as the logical effort. So G is called as the logical effort, measures the relative ability of the gate to deliver a current. So of course we will just try to find out what is this G. So G is nothing but the logical effort. So G is equal to 1 for an inverter. We shall actually take some examples and try to identify what is the value of G for different gates. And this H is nothing but the electrical effort. So electrical effort is nothing but C out by C in. is the ratio of output to the input capacitance, sometimes also called as fan out. So let us just try to see what is this G. G is nothing but the logical effort, and H is given by the electrical effort. The logical effort multiplied by electrical effort happens to be the stage effort or the delay effort. So we shall have a look at, of course, what is this P. So we know that this delay is given by F plus P, where F is given by uh, the effort delay, or nothing but if you know that this is effort delay or the stage effort, which is given by G into H. Now what is this P? P nothing but the parasitic delay. So P is represents the delay of the gate driving no load. So because we are talking about the parasitic, so when there is no load, what is the delay caused in driving such a load, which is having no load? So this is set by the internal parasitic capacitance. Now let us, before we go to this, we should just look at how do we estimate this G. So as we know that, let me just take up an example and try to find out how do we estimate the value of G. Okay, let us try to find out, okay, how do we estimate the logical effort of basic gate. So in this case, okay, we have an inverter. Now it was said in the previous slide that, okay, logical effort of inverter is equal to 1. So this is what is said here. So it was said that, okay, G is equal to 1 for inverter. So we shall see that, okay, how it is 1. Now you can see now. So this is the structure of an inverter. We have NMOS here, PMOS here, and we shall assume that. So the value of Kp of this is around 200 microampere per volt square. So this is 100 microampere per volt square, meaning the dimension of your PMOS is made twice of the NMOS, so that the charging time and discharging time happens to be the same. So this is what we discussed. The scaling, the P type is always twice that of the N type, because the mobility of a hole, we are considering half of that of the mobility of the electron. Now we are saying that 2 is the unit dimension of PMOS and 1 is the unit dimension of the NMOS. So if you can actually see what is the input capacitance, so since it is scaled by 2 times compared to this, so we should take the input capacitance at the P type as a 2 unit and at the N type as 1 unit. So C in of the inverter happens, because these two are coming in parallel, so this happens to be 3 unit. So C in of your inverter happens to be 3 unit. So we'll define what is the G, that is logical effort of basic gate. So if you want to define what is the G of the inverter, now it is C in of the inverter divided by C in of the inverter. Now whenever we're defining the logical effort, we take the reference of an inverter. So when we are trying to find the logical effort of the inverter itself, now it is C in of the inverter divided by C in of the inverter. Now in this case, we know that C in of the inverter is 3. That is nothing but the capacitance of the input of your inverter is 3. And since we are finding the G of the inverter itself, now it is 3 by 3. So that's why G happens to be 1 here. So that's what we said in the slide here. So G is equal to 1. So G for an inverter is equal to 1. Now we should try to see what is the G of a NAND gate, which is a 2-input NAND gate. Now we know that G is defined as C in of the gate divided by C in of the inverter. Now since we know that in order to have the rise time and fall time of this NAND gate equal to that of the inverter, we have scaled the NMOS transistor by 2 times, so that the Rn, the total Rn of this is exactly Rn, that is each transistor is contributing half of the resistance compared to this. Now it is Rn by 2 plus of Rn by 2, the entire thing happens to be Rn. Now you can see now this is scaled by 2 times and this is 2, 2, because they are in parallel. So if you can actually see what is the input capacitance of this NAND gate, which is a 2-input NAND gate, so it is 2 unit plus 2 unit. So that's what is C in of the NAND gate is 2 plus 2, which is equal to 4 unit. So this is about C in of the gate, so divided by C in of the inverter. Now it is 4 by 3. So that's what is we have here. This is logical effort of the NAND gate, 2-input NAND gate is, this is 4 by 3. So why it is 3 means because for the inverter it is 3, for the 2 input NAND gate it is 2 plus 2 which is 4. So it is 4 by 3 now. Now similarly we can find what is for the, let us just see what is, this is for a 3 input NOR gate. Now you can see we are connecting a 3 input NOR gate. So now it is scaled by 3 times because we have 3 transistors in series here. So it was actually 2 here for the inverter. Now it is 3 stack. Now it will be 6 6 6 now. Now it is, they are in parallel. You can just retain the dimension this as 1. So as you can see now, this is 6, this is 1. The overall Cin of the NOR gate is 7. So Cin of NOR 3 is 7. Cin of the inverter is 3. Now it is 7 by 3. Meaning to say, in general, so if the number of gates of an OR gate is n, so we write G of an OR gate as 2n plus 1 by 3. So whereas in case of the NAND gate, it happens to be, as you can see here, it is n plus 2 by 3. So it is n plus 2 by 3, here it is 2n plus 1 by 3. So this is how do we estimate the value of G for any given gate. That's what we have here. So we have this. Now this is what is this is what for the inverter. Now it is scaled by 1. This is scaled by 2. This is a 2 input NAND gate. Now it is 2 2. This is also 2 2. This is a 2 input NOR gate. Now we can see this is scaled by 4. Now you can see G of the inverter is 3 by 3, which is nothing but 3 of the inverter by 3 of the inverter. Now for the NAND gate, 2 input NAND gate, it is 2 plus 2 divided by 3. Now for the 2 input NOR gate, it is 1 plus 4, which is 5 divided by 3. That's what we saw in the example. It is 2n plus 1 by 3. So 2n plus 1 is 5. 5 by 3. Here it is n plus 2 by 3. So n plus 2 is 4 by 3. So this way we can estimate what is the G of a given logic gate. Now once we know what is G of a logic gate, we can certainly estimate what is the total D, that is D is given by F plus P. First we shall also have a look at okay, how do we estimate the value of P before we go to estimating the final D value. So let me just try to find out how do we estimate the value of P now. So P is, as you know, that it is a parasitic delay. So P is given by C intrinsic of the gate divided by C intrinsic of the inverter. Now this is the parasitic delay, which is again the ratio of P intrinsic of the gate. This is the C intrinsic of the gate divided by C intrinsic of the inverter. If you can see now, intrinsic impedance at the output is given by, this is 2 unit, this is 1 unit, now it is 3 unit. For the inverter, it is the 3 by 3, which happens to be 1. If you can actually see what is the P of a NAND gate, which is a 2 input NAND gate. If you actually see at this node, so it is 2 unit, 2 unit and 2 unit. So totally we have 6 units of intrinsic capacitance over here. So that's why C intrinsic NAND 2 is 2 plus 2 plus 2, which is 6 here. So it is 2 plus 2 plus 2, which is 6. So what is the parasitic delay of the inverter is nothing but C intrinsic of the NAND gate, which is 6 divided by C intrinsic of the inverter, which is 3. So meaning if we have a 2 input NAND gate, the P of that NAND gate happens to be C intrinsic of the NAND gate divided by C intrinsic of the inverter, which is 6 by 3. Similarly, we can find what is the P intrinsic of the NOR gate. P intrinsic of the NOR gate is again given by, now since it is NOR, it is on the pull-up side we have 3 transistors stacked up. It is 6 6 6 here. So the nodes which are connected, the output is 6 here, 1 1 1. So it is 6 plus 1 plus 1, which is 9. So P of the inverter, P of the NOR gate, 3 input NOR gate is 9 by 3. That is, this is 9 here divided by 3. This way we can estimate the value of p of different gates depending on the number of bits.